Imagine a world so tiny that the rules of everyday life collapse. A world where an electron, trapped in an invisible prison only a billionth of a meter wide, can never sit still, and its energy comes in sharp, discrete steps like the rungs of a ladder. This isn't science fiction. It's quantum mechanics. And today, we're going to explore one of its most iconic problems: the particle in a box. By the end of this video, you'll see exactly how we calculate the first 3 quantum energy levels for an electron confined in a 1 nanometer box. Before we get too deep into this topic, be sure to like this video and subscribe to the channel. This helps to bring more valuable content to the platform for your knowledge and understanding. Remember, knowledge is power. Now back to the episode. To start, let's picture the box. It's not a box in the everyday sense. There are no walls or hinges. Instead, think of it as a region of space 1 nanometer wide, about 100,000 times smaller than the width of a human hair. Inside this box, the electron is free to move. But at the edges, the walls are infinitely steep. That means the electron cannot escape. It's trapped, bouncing back and forth in the quantum void. Now, in classical physics, you might expect the electron to have any energy it likes depending on how fast it's moving. But in the quantum world, the story is very different. The electron can only exist in certain states. These are the famous quantized energy levels. So, how do we find those levels? The rulebook comes from the Schrödinger equation. Solving it for this infinite box gives us a simple formula: En equals n squared h squared divided by 8 ml squared. Here's what it means. En is the energy of the nth level. H is Planck's constant, a tiny number that governs quantum action. M is the mass of the particle, in our case, the electron. L is the length of the box, and n is a whole number, 1, 2, 3, and so on. No fractions, no decimals, just neat, discrete steps. This is like having a ladder where you can stand only on the rungs, never in between. The first rung is n equals 1, the ground state. Then n equals 2, the first excited state, and so on. Now let's calculate. We'll use Planck's constant, 6.626 times 10 to the negative 34th joules per second. Electron mass, 9.11 times 10 to the negative 31 kilograms. Box length, 1.0 times 10 to the negative 9th meters. Step 1. Calculate the constant piece, h squared divided by 8 ml squared. Do the math, and we get about 6.02 times 10 to the negative 20th joules. That's the energy of the ground state, E1, but physicists like to talk in electron volts, not joules. 1 electron volt is 1.602 times 10 to the negative 19th joules. Converting gives us E1 equals 0.376 electron volts. That's the first rung on our quantum ladder. Now, the beauty of this formula is that the energies scale as n squared. So, E2 equals 4 times. E1 equals 1.504 electron volts. E3 equals 9 times. E1 equals 3.384 electron volts. And there we have it, the first 3 energy levels of an electron trapped in a 1 nanometer box. At first glance, these numbers might seem abstract, but let's put them into context. 0.376 electron volts. That's tiny compared to the energy in a chemical bond, which is a few electron volts. But notice how quickly the levels rise. By the time we reach n equals 3, we're already above 3 electron volts, in the range where visible light photons live. This means that transitions between these levels, say, an electron jumping from n equals 3 down to n equals 1, would release energy as light. In fact, this simple particle-in-a-box model is the foundation for understanding quantum dots. Nanoscopic crystals that glow with brilliant colors because their size controls the spacing of energy levels. The particle in a box also teaches us something profound about the nature of quantum reality. The electron can never rest at zero energy. Even in the ground state, it carries a finite amount of energy. This is the essence of the uncertainty principle. The electron cannot be perfectly still or perfectly localized. Confinement forces motion, and the tighter the box, the higher the energy. Shrink the box to half a nanometer, and the energies shoot up by a factor of 4. Quantum mechanics tells us, the smaller the world, the more violent the quantum dance. Now we've only looked at the first 3 energy levels, but the ladder continues infinitely upward. N equals 4, n equals 5, n equals 6, each with its energy given by n squared times the ground state. In practice, higher levels become harder to observe, because electrons tend to relax quickly down to lower states, releasing energy as photons or heat. But in principle, the ladder goes on forever. And this infinite ladder of energies, emerging from the simplest of assumptions, shows just how elegant quantum mechanics can be. So, why do physicists love this problem? Because it's not just an academic toy. It's a gateway to understanding the quantum world. It explains why electrons in atoms can only occupy certain orbitals. It lays the groundwork for quantum wells and semiconductors, the technology behind lasers and LEDs. And it gives us insight into nanotechnology, where confinement effects dominate. Every time you look at a smartphone screen or see the glow of a quantum dot TV, you're witnessing the particle in a box come to life. To recap, we imagined an electron trapped in a 1 nanometer box. We used the formula En equals n squared h squared divided by 8 ml squared. We found the first 3 energy levels, 0.376, 1.504, and 3.384 electron volts. And in the process, we discovered a model that's simple, elegant, and surprisingly powerful. So next time you hear about quantum dots, lasers, or even the mysterious quantum realm, remember, it all starts with something as humble as a particle in a box. Thanks for watching. If you enjoyed this journey into the quantum world, hit like, subscribe, and share this video. And let me know in the comments, which quantum topic should we explore next?